Waterborne plastic waste is now a global concern, with potentially harmful discarded plastic fragments contaminating almost all coastal and marine ecosystems. Our thesis, Plastic, is an investigation into the scalar disparities of plastic pollution and a speculation into how architectural systems can be utilized to engage with that disparity of scale. While the extent and severity of plastic pollution is widely known, very little has been done to address the vast quantities of plastic present in the world's oceans. What makes oceanic plastics so difficult to manage are the ways in which plastic pollutants simultaneously interact with the environment at both a macroscopic and microscopic scale. On a macro scale, ocean-borne plastics get carried by currents into 5 colossal plastic patches. The largest of these patches is the Great Pacific Garbage Patch that spans over an area 3 times the size of France. On a micro scale, the plastic fragments within the oceans degrade into smaller and smaller pieces until they become easily ingestible particles called microplastics. Microplastics are classified as particles below 5 mm in diameter and consist of fragments, fibers, films, and pellets that are highly pervasive and almost invisible to the naked eye. The extreme disparity between the minute scales of plastic pollutants and their colossal areas of contamination makes it challenging for humans to adequately comprehend, let alone manage. Our thesis situates architecture as a medium through which both of these scales of plastic pollution can be addressed, as a tool through which plastic pollutants can be consolidated into a manageable and perceptible scale. Our project aims to develop architectural systems for the extraction and long-term managed storage of aquatic plastic pollutants. Our method of achieving this is through the recycling of plastics from rapidly disposable items into architectural elements that can exist for decades before needing to be disposed of. The project has 2 sites that are strongly interlinked despite their geographic separation. Our initial site of intervention focuses on the heart of the Pacific Garbage Patch, which has the highest density of plastic debris. Our secondary site focuses on urban river mouths, where 80% of mismanaged plastics enter the ocean. To collect and consolidate plastic debris from the Pacific Patch, we considered retrofitting derelict oil rigs to form a network of plastic collection and recycling hubs. Each oil rig would be stripped of drilling equipment and instead be outfitted with an array of collection nets, sorting, and storage equipment. However, while we have faith in the efficacy of this system in gathering oceanic plastics, the site's remoteness offered little opportunity for human engagement with the problem itself. Therefore, the site became difficult for continued architectural exploration and innovation. In response to this revelation, we instead shifted our focus towards urban river mouths. Our site of intervention is the LA River, which leaches more plastic into the Pacific than any other river in the US. The LA River at one point ran along a wild alluvial plain, which provided a terrestrial expanse for it to deposit sediments. However, as LA continued to develop around it, the previously meandering river was engineered into a linear canal, designed to efficiently direct stormwater surges into the sea. This indirectly transformed the river into a superhighway for urban debris and contaminants into the ocean, much of which includes plastics and urban waste. As urban runoff continues to accumulate downstream, we chose to implement our intervention along the mouth of the LA River, where there would be the greatest abundance of plastic sediments. Our site is now at the derelict eastern flank of the LA port. We began our intervention by redirecting the flow of the LA River through our site. To slow down the flow of water, we split the river into a series of smaller streams, forming an artificial delta. In order to sequester the larger macroplastic sediments, we designed a compact collection center to the north of the site. The vast majority of the site, however, was transformed into an artificial wetland, designed to sequester the more pervasive and smaller microplastic sediments that cannot be filtered efficiently from the water. To the north of the site, the plastic processing plant collects, sorts, and converts large river plastic sediments into compressed plastic panels. To the south, A large array of plant filters sequester microplastics within their biomass and are then securely composted on site. The northern structures use existing systems of river plastic sequestration and sorting to produce bales of relatively pure plastic-based materials. These bales are then converted into structural plastic panels that are then used to construct the enclosure of the collection center itself. The process of constructing these panels is very simple, and we were able to experiment in creating our own prototype panel with household equipment and plastic waste. Gathered plastics were shredded, melted, and then molded to form dense panels that are malleable when heated but sturdy when at room temperature. Our structures envision the creation of massive corrugated panels of compressed plastic to be used to form structural architectural enclosures. The color and texture of each panel will be dependent on the plastics that were compressed to form them, giving each panel its own unique identity. Each prefabricated panel would then be heated on site to make it malleable, and then be manually bent and applied upon one another, allowing for the creation of free-form structures from prefabricated elements. While each panel wouldn't be able to self-support to one another, the sequential lamination of multiple layers of plastic can eventually develop into complex massing structures. The aim in doing this is to be purposefully excessive and inefficient in our material usage, so that more plastics can be stored within the thickness of the structure itself. Continued lamination of these panels will force the structure to expand over time, becoming a physical record for the amount of plastic flowing in the LA River. The south of the site consists of both the microplastic sequestration wetland and a cycle superhighway to curate the scale of plastic pollution to the public. The central wetland islands comprise the cycle superhighway that acts as the primary connection of the site to the broader urban fabric of LA, a publicly accessible buffer zone that offers public amenities like parkland, floating wetland pads that are used for sequestering microplastics into plant roots, and finally, a series of composting bunkers that are used to securely store contaminated biomass until it decomposes into soil. The floating wetlands make use of a novel filtration system that we are in the process of developing alongside other researchers at Princeton University. Each pad consists of a layer of compost to supply plants with nutrients, a removable porous membrane for inserting plant species, and a fiberglass frame to protect the pads from fast currents. To showcase how plant roots can sequester microplastic, we experimented with homegrown duckweed. As seen here, plant roots exude a gelatinous film that can entrap small sediments like microplastics. Bacteria on the film can then digest the microplastics into the plant matter. By creating a dense network of underwater plant roots, microplastics become entrapped and sequestered without disturbing aquatic wildlife. Once plant material becomes saturated with microplastics, drones can be deployed to transport contaminated biomatter into the center of each island, forming a composting mound. To keep this toxic biomatter away from wildlife and the ocean, each mound will be encased in a plastic sarcophagus. Over time, these plastic sarcophagi will continue to grow and swell as more and more biomass is piled up. The site ultimately serves to consolidate plastic sediments from vast geographies of minute fragments into a dense nucleation of plastic landscapes and architecture. Through its continued growth and mutation, the site becomes a lifeform for the accumulation and eventual digestion of plastic pollutants. As societies gradually transition away from plastics towards less harmful alternatives, we anticipate the growth of the site to stagnate, transforming it into an artifact of bygone plastic consumption, all the while locking away plastics within the thickness of the city.